Okay, hi guys. So we'll be continuing on comparing rates of electrophoretic aromatic substitution reactions in the following compounds. So let's get started with the next example. So we have something like this. And this compound. This, and finally this. Okay. So what would be the rate? Again 1, 2, 3, 4. And why is this the case? More plus H, then little less plus H, less number of alpha hydrogen, and then 0 alpha hydrogen. Let's see for this compound. Aniline. You can also have NO2 first, then aniline, then we can have something like a amide group with N attached to the phenyl ring, and last we have something like this CS3. Okay, so this is deactivating. Okay, this is also deactivating, but this will be directing ortho and para, and this will be directing at meta position, because this nitrogen would have no lone pair and this have actually one lone pair, but still these two are deactivating. So we would be having something like 3 then 1. Okay, and then actually we have something like actually I think we have I have written something wrong here. This is or read something wrong here. This is actually not deactivating, this is activating group only. Okay, had it been something like this where oxygen is directly attached to nitrogen atom, then it would have been a deactivating group. In this case, it can either go to either donate its lone pair to this bond and get oxygen negative charge, or it can donate it to the phenyl ring. Obviously the rate would be lesser than the second compound, which is the highest in terms of activating, but both these compounds are actually plus M effects only. In this case, the lone pair was actually can actually be participating in resonance with the neighboring CO group, but in this case it would definitely participate with the electrons on the nitrogen atom would definitely go in the resonance with the phenyl ring itself. Hence the plus M on aniline would be greater than plus M on this compound. Okay, hence 2 would be more than 3. This is not deactivating. My bad for seeing this as a deactivating group. Okay, and then we have something like the fourth one. Okay, then the first one. Okay, now let's see this example. We have something like this compound, and we have something like this one, and then we have a simple benzene ring. So obviously, as there is a presence of 2 alpha hydrogens on here, so 1 would be greater than 2, would be greater than 3. On 2 we actually have a plus M from the neighboring phenyl ring, hence 2 would be more than 3. Okay, let me write down some note here that biphenyl, I am talking about this, is more reactive than benzene in electrophilic aromatic substitution because of plus M on one phenyl ring because of plus M due to another phenyl. I just wrote it wrong here. Because of plus M due to another phenyl ring or attached phenyl ring. Okay, attached benzene, or you can directly write phenyl ring. Okay, so let's see another example. So we have something like this. This compound, and finally we have something like this. So compare the rate of electrophilic aromatic substitution. So obviously in this case everything is determined here in terms of inductive effect only. Okay, so more the number of substituents, or more the number of more the number of substituents attached to benzene ring, as all are CS ring in this case, more will be the plus ion these places. Okay, so the order would be simple: 1 2 3 4. Okay, so and how is actually this internally happening? Suppose we have CS3 at this carbon and this carbon, as in the second case we have something like this. Now electrophilic addition substitution reaction takes place. First the addition will take place. So let's suppose electrophile is added at this position. We get a positive charge here, double bond here and double bond here, and CS3. Okay, hence this would be stable, because this intermediate would be stable because we have a positive charge and it is actually resonance stabilized, and on the top of it we have inductive effect stability as well. So one important point to note here is that meta is more stable, is more reactive than paraxylene towards electrophilic aromatic substitution reaction, because one methyl will reinforce the other. Okay, so I just write first of all what is metaxylene and paraxylene. This is metaxylene and this is paraxylene. Okay, so we saw this case in metaxylene, that first of all let me also draw the structure of the intermediate that would be there in case of paraxylene. So we have something like E here and CH3 here. Okay, and let's draw the double bond as well. So in this case the electrophile was added at this position and the positive charge comes to this place, and inductive effect for this case would be high. But when you compare the inductive effect due to this CH3 group, it would be much lesser, because it is 1 2 3 carbon distance away. Okay, while in case of metaxylene structure, metaxylene carbocation formation, we have something like positive charge at this carbon position, which is 2 carbon distance away. Okay, so in case of metaxylene intermediate, the other CH3 group, which was this in this case and this in this case, is having more inductive effect on the carbocation. Okay, hence metaxylene is the other CH3 group of metaxylene is also contributing to the stability of carbocation, which was added to the ortho position of the other CH3 group, in this case this CH3 group. Okay, so let me write it down formally, that metaxylene is more reactive than paraxylene towards electrophilic aromatic substitution, because the other methyl or the other CH3 group or methyl group also participates inductively in the stability of intermediate arenium ion, also known as Wheeler intermediate. Okay, so with this note we come to an end of this lecture. In the next lecture we'll be seeing Fiddlecraft alkylation. Okay, so till then, good luck and goodbye.